Welcome to Citizen Science, stories of science we can do together, brought to you by SciStarter. In this episode, we'll hear from NASA researchers we caught up with at the recent Citizen Science Association annual conference known as CSci in scenic and extremely toasty Tempe, Arizona. A couple of weeks ago, Tempe, Arizona was the absolute hotbed of citizen science activity. And when I say hotbed, I mean hotbed because it was like 100 degrees every day there. But it's also true figuratively because hundreds of citizen science project leaders from universities and federal laboratories, libraries, and various nonprofit groups all gathered for the National Citizen Science Association conference, now dubbed CSci. So capital C asterisk Sci, S-C-I, which is really clever because the C can stand for citizen science, but if you don't like that term, you can make the C stand for whatever you like better. Community science or, I don't know, collaborative science. I think I just made that one up, but who knows? Anyway, it all amounts to regular non-scientists helping professional scientists with their research. And when you think about that, maybe groups like Audubon with their bird counts or Journey North with their monarch butterfly and hummingbird migration tracking, or the National Weather Service with their weather watcher networks, those sorts of things come to mind. And you might be surprised to hear that one of the biggest players in sea science is NASA. NASA currently has 36 active citizen science projects where you can help their scientists study everything from exoplanets orbiting distant stars to potential mosquito outbreaks here on Earth. I spoke with NASA's head of citizen science programs, Marc Kuchner. So Marc, what can you tell us about this program?
NASA's citizen science program is where scientists work with volunteers from around the world and accomplish science that requires help from the passion, the intellect of our volunteers.
And you guys already have the top scientists in the world. So what can regular people contribute that they can use that could be helpful?
Our scientists are awesome, aren't they? Our volunteers are even more awesome because they think of things that our scientists overlook. You know, sometimes the great aha moments in science are when a scientist starts down one path and then all of a sudden realizes that, oh, wait, there was another discovery lying just over there. And, you know, real human brains, real curious humans will naturally go gravitate to in the new direction, right? And so having volunteers bring that curiosity makes science go.
And what sorts of projects can we help out with?
Yeah, so that's only just the start of it. Our projects benefit from people who are in locations that are special. So for example, it can be challenging to send like thousands of NASA scientists to remote parts of the globe to study penguins or to study an aurora. But people who are there can pick up their camera and go outside and take the right picture at the right time and make a huge difference. Wow.
So how can people get involved? I know you already have, I guess, millions of folks that are doing this. For people watching this video, what do they do to join one of these?
science.nasa.gov/citizenscience lists all of our 36 active projects. And just pick your favorite science topic and start clicking buttons and see where it goes.
Great. All right, thanks so much, Marc.
It's my pleasure.
Now, nothing gets Marc and other NASA scientists more excited than space events that are visible and compelling to people here on Earth. And high on that list is solar eclipses and auroras. They're events, they're beautiful, they're dramatic, and most of all, they're visible to people without the need for telescopes or other special gear. And that's why NASA folks are like hyperventilating about the coming year, which they're calling the heliophysics big year. Helio meaning sun, physics meaning the study of physical phenomena, big meaning big, and year, Okay, you get the idea. This is going to be a big year for solar science. We've got an annular eclipse known as the Ring of Fire eclipse that's happening on October 14th of this year. That is a solar eclipse that happens when the moon is sort of at its most distant point in its orbit from Earth. So it doesn't completely cover the sun. It leaves a ring, a circle of the corona visible as like a bright ring, hence the name. And it looks really cool. And then there's the total solar eclipse where the moon is close enough to Earth that the disk completely blocks the sun. The solar eclipse is sort of traversing the middle of the United States on April 8th of 2024. And not only that, but we're also coming up on what's known as the solar maximum portion of the sun's 11-year solar cycle. And that means crazy cool auroras in both the northern and the southern hemispheres. So both the Aurora Borealis and Aurora Australis. So NASA scientists right now have an especially sunny disposition. Oh boy. Okay. Anyway, that includes Amir Caspi, who is principal scientist on the Citizen CATE project. That stands for the Citizen Continental America Telescope Eclipse Experiment. He's trying to sign up 34 teams of amateur astronomers who live along the April eclipse's path of totality. Thanks for being with us, Amir.
Hi, thanks for having me.
And what can you tell us about CATE?
So Citizen CATE 2024 is a scientific project to understand the sun's outermost atmosphere, the solar corona, during the total solar eclipse that crosses the United States on April 8th, 2024. Solar eclipses are actually an amazing way to understand the solar corona. You can't see it during the day normally because the sun is just so bright.
Right.
But during a total eclipse, the moon crosses in front of the sun and it blocks out the really bright disk. And that lets you see the solar corona, which is only about as bright as a full moon. And during a total eclipse, you can see it in resolution and quality that you just can't match any other time. So it's a perfect opportunity to study the corona.
Wow. And so who are the volunteers that are going to be helping you with this? How do you select them? What are they going to be doing? Yeah.
Well, we're still working on our recruitment strategy, but the plan is to have 35 teams of about 3 or 4 people each in communities all along the eclipse path, starting in Texas, going through the Midwest, all the way up into Maine.
Okay.
We're going to have about 35 teams each, 35 teams total. And each team is going to be separated by about 50 miles or so that they span the eclipse path. And as the shadow progresses across the United States, it crosses each team sequentially.
Okay.
And so we're going to give equipment to each team. We're going to give them cameras, telescopes, tripods, computers, and we're going to give them training so that they can take observations of the solar corona uniformly, exactly the same as every other team. The reason we want to do that, if you're standing in just one location, the eclipse is only going to last a few minutes. The shadow will pass over you and you'll get a few minutes. It's an amazing experience, by the way. But we want to study the corona, we need more than just a few minutes of observations. So if we can take advantage of the fact that the eclipse spends 60 minutes over the United States, then we can get a time-lapse movie, basically, of the corona. And so if we have stations all along the eclipse path, and they're all taking data with the same equipment in the same way, we can then splice all of that data together and get 60 minutes of totality.
Wow. So I know this is for a lay audience, but I just wonder if you could explain, what sort of data you get and what you do with it.
Right. So the cameras that we're going to be using are just regular cameras, but they are special because they're sensitive to polarized light. So if you have polarized sunglasses, for example, you know that they cut out light reflections in a certain way. And that's because light is a wave, and it can be polarized. In other words, the wave can do this or it can do this. And you can actually tell which way the wave is waving by using special filters. So this camera has special filters that tell us what the polarization of light is. And everybody will be using those special cameras. The reason that we want to make these measurements is because the solar corona, it turns out, is really, really hot. The surface of the sun, it's only a few thousand degrees, but the corona is a few million degrees.
Oh, wow. That's so weird.
Yeah, it's really weird. It's like if you're standing next to a campfire and you walk further away, it gets hotter and hotter and hotter. And that's not something that we're used to. So we're trying to understand why the corona is so hot. And the corona also has a lot of magnetic field all through it. So, everyone's hopefully familiar with bar magnets, fridge magnets, right? And in school, you probably did this experiment where you put a piece of paper over a magnet and you spread iron filings, and you notice that it makes specific shapes. It traces out the magnetic field.
Right.
So in the sun, there's hot plasma, gas that's had its electrons stripped off of it. And it traces out the shape of the magnetic fields in the sun, allows us to see what that looks like. That magnetic field is super duper complicated, and it changes over time. And sometimes it can actually snap and cause solar flares. We're still trying to understand all of those processes. And during a total solar eclipse, when we can see the corona so clearly, that's a best time to study the sun's magnetic field, to study the plasma that's in the sun's outermost atmosphere, how it changes, how it evolves, what powers it. And also, the sun puts out a constant stream of particles called the solar wind. So basically, it's shooting off electrons and atoms all into space. Those hit Earth. Sometimes they cause the aurora. And we're still trying to understand why those particles come off of the sun and how. Again, during the total solar eclipse, we'll be able to see processes that help us better understand.
Oh, that's so cool. I mean, normally you want to turn the light on and shine to learn more. In this case, when it goes dark, you can actually have this glimpse of things you can't normally see.
Yeah, that's right, because we're trying to see something really dim.
Yeah.
And so you have to turn off the really bright thing first. Yeah.
Oh, that is so cool. So what's that date again?
That's April 8, 2024.
Okay.
Yeah, and it crosses from, in the United States, it crosses from southwest Texas around San Antonio all the way through southern Illinois, Indiana, and up into Niagara Falls, Rochester, Buffalo, and then out through Maine.
Cool. All right. Well, thanks so much, Amir. That sounds awesome.
Yeah, thanks for having me.
Also part of the heliophysics big year are studies about the aurora, which occur in both the northern and southern hemisphere. Liz McDonald heads up a citizen science project called Aurorasaurus, for no particular reason, where people share images and reports of the aurora borealis in the north and the aurora australis in the south. So Liz, tell us about Aurorasaurus.
Yeah, so we work with people who photograph the aurora and tell us about it, and we can build better alerts for when you can see aurora. And we've made discoveries about unusual kinds of aurora called Steve.
Steve? How? Okay. Wait, let's back up for a second. Aurorasaurus, is that just a cute name, or is there something prehistoric about this?
It is just a cute name, but memorable, hopefully. And, that's, we came up with the name back when we started in 2014. Before that, it was really hard to come up with a name, but I'm really glad that we all liked this one.
Right. Yeah. Okay, but Steve, is that just because it was discovered by Steve, or you have a friend named Steve?
Yeah, good question. So there's actually a movie called Over the Hedge.
Okay.
And in that movie, there's animated characters, and there's a little squirrel voiced by Steve Carell, and there's a hedge that appears in their neighborhood, and they're afraid of it. And so he says, let's just call it Steve, because we don't know what it is. And so people were noticing this weird, different kind of aurora while they were watching aurora to the north from southern Canada, especially Alberta. And there was this thing overhead that was mauve colored and looked like a contrail, other than it being mauve with some green fingers waving around it. And it was, we needed a name. So they said, let's just call it Steve. And that name stuck.
Wow. So now, for the people who contribute, what do you do with their data? How is it useful in the study of, I guess, the aurora and the magnetosphere and all that, to get information back from regular people?
Yeah, so we actually do not know nearly enough. We don't have nearly enough satellites. Space is way too huge. We don't have a real-time view of the aurora all the time. And then the aurora can be very dynamic. So it can come and be visible even here in Arizona, but for a very brief amount of time and very rarely. And so now using smartphones, we can report if you've seen it and let others know around you. And that is, then we can all see this beautiful phenomena, this example of space physics. And it's really exciting to capture.
Wow. So is it possible that people will find new phenomena? So in addition to Steve, we'll have, I don't know, Carol and Rita and Fred?
Alan is actually the new name for a possible thing being looked at right now from another group of aurora chasers based in the southern hemisphere. So the Aurora Australis folks have seen something that we're working on the name, but there's a joke about Steve and Alan. I don't know. But yeah, you could be the next one, and it would be fun, I think, to...
I want to name it Bob.
Yeah.
I have my own aurora phenomena.
Then you need to sign up and get cracking on looking for that unusual aurora.
It's a really dynamic kind of system. Do you know what mostly, if there is an answer to this, is generating the variation as it changes in the sun, changes in the upper atmosphere, magnetosphere, changes in the core of the Earth? What spins off Steve's and Alan's and things like that?
All of those things change all of the time. But the primary thing is that the Earth is in its protective magnetic bubble. And so the Earth's North Pole and South Pole are pretty constant. And so our bubble always has a fixed North and South Pole. The sun's magnetic field has a North and South Pole that actually flip every 11 years. And that causes the solar cycle, which causes changes that drive more aurora during the maximum of that cycle. And then also there's out in space where the sun's magnetic field, it extends throughout the planets. And then where it interacts with the Earth's bubble magnetosphere, it can change. It can be north or south or east or west or strongly blowing from the sun or not. So the Earth's magnetic field environment is bathed in this constantly varying solar wind, and that drives the constantly varying Steve's and Alan's.
It really is like weather.
Aurora.
You have things popping up.
Space weather.
Yeah, exactly.
It is called space weather.
Just as dynamic and just as ever-changing and interesting. Wow.
Yeah. And it's a 93 million mile system that's hard to model because we are looking at it from here and the sun is a long way away and a lot of things can happen along the way, which is why it's hard for us to give you we can see things happening on the sun and we know it'll take about 3 days to get here. But then until we have some satellites that are closer to Earth, 1 million miles away, which is about an hour at the speed those things travel, we can't really tell you how strong it will be or exactly where the auroras will happen.
Wow. All right. Incredible. All right. Well, thanks so much, Liz.
Thank you, Bob.
All right, we'll have lots more about the heliophysics big year and many citizen science projects associated with it in the coming months. Now, NASA doesn't shy away from big questions, and this next NASA citizen science project asks one of the biggest. Are we alone in the universe? UCLA doctoral scholar Megan Grace Lee works on the project. So, how are you finding out whether we are alone in the universe, and how can we help?
That is a great question.
That is the question.
Yes.
Right?
So every year we search the sky for radio signals, and we look for radio signals because nothing else in space is really generating signals that look like this. The only known generators we have are pulsars, which are quite rare, and we can generally figure out this is a pulsar, or other people on Earth sending radio signals. So we have over 60 million candidate technosignatures that we found over the past 7 years. And our current computers can get rid of 99.5% of these candidate signals and say these are for sure from Earth. But that leaves 0.5% of the most interesting signals.
And how many is that? I can't do that.
300,000.
Oh, thank you. Okay.
So you could have your grad student, aka me, search through all 300,000 of these signals and try to tell you if they're from Earth or not, or we could eventually train an AI to do that for us. So that is our goal with the Citizen Science Project.
Oh, okay. So it's not just that we're going to get thousands and thousands of people to identify them and that's it. They're training a computer to do it, so in the future you could do even more of this.
Yeah, that's exactly correct, because the search volume is already so much data, but we've only searched a bathtub's worth of the Earth's oceans, if you try to compare that to how much of the sky we've searched. Wow. So we really need like a lot of computing power and, you know, hopefully eventually not as much manual labor from all of us. But yeah.
Well, what is that? So how do what's the task that I do when I sign up?
So you are handed a dynamic spectra, which is a fancy word for a frequency versus time graph.
That's also fancy.
That's also true. So we visualize our radio signals in terms of some kind of image. Okay. So normally you maybe hear these things or the computer would read them, but we make them into pictures so you can visualize a radio signal, which is a little weird. Okay. Yeah, so our radio signals sometimes look like diagonal lines, they can look like polka dots, they can be like weird plaid shapes. Some of them look like landing strips, caterpillars. And so we just ask you to choose which image it looks most like. So we have some representative image of all the different classes. You know, there's like a fat caterpillar, some straight lines, some pinstripes, and you just decide which image yours looks most like.
Oh, okay.
Yeah.
And then, so what is that? So caterpillar is something that some ham radio operator did, and a straight line is something that...
Exactly.
Oh, okay. And then if it's none of the above, it might be...
Yes.
Might be
so
an alien civilization saying, why aren't you listening to me? We've been doing this for 1,000 years.
I know, right? Dumb humans. But, so our none of the above class is actually our third most populous class. There are thousands and thousands of none of the above. So these could be really rare radio transmitters, maybe somebody, you know, one ham radio person versus the GPS created this thing that's none of the above.
Okay. And then so are the none of the aboves further analyzed?
That's correct,
okay.
Yeah. So every single none of the above class eventually will be looked at by a member of our team, meaning either me or my advisor, Jean-Luc Margot.
Okay, all right. And then in some distant future, there'll be a computer program that just gets it down to those 300,000 get down even tighter.
Exactly.
So you don't have to look through quite as many.
So I guess my hope is that the next graduate student who takes on this project is looking at much fewer than 300,000. And then, you know, maybe someday it's 10 and then it's 1 and we found them.
Yay. All right. Great. Well, thanks so much for sharing with us.
Thank you. Yeah.
Well, if any aliens are listening into this podcast, why not hit us up at info@SciStarter.org. Let us know what you want to hear on the podcast and tell us why you waited so long to communicate with us. And that goes for Earthlings too. We'd love to hear from you as well. Tell us what you think of the podcast, what you'd like us to cover in future episodes. Ask us anything. All right, well, in this episode, we've told you about just 3 of the 36 active NASA citizen science projects available, which is totally inadequate. Fortunately, I can announce that SciStarter has a new partnership with NASA to share much more about NASA citizen science, and it's called Do NASA Science Live. It consists of regular live seminars where you can hear about NASA citizen science programs from the project scientists themselves, live, interact directly with them, ask them questions, whatever you like. Now, the first Do NASA Science Live event is July 20th, and we're co-presenting that one with NSTA, the National Science Teachers Association. To learn more about that event and other NASA citizen science stuff, go to SciStarter.org/NASA. Well, that's all we have for you this episode. Happy summer. I'm Bob Hirshon. See you next time. This podcast is brought to you each month by SciStarter, where you will find thousands of citizen science projects, events, and tools. It's all at SciStarter.org, SciStarter.org. SciStarter's founder is Darlene Cavalier. And thanks so much to you, the listener and citizen scientist, for getting involved and making a difference. If you have any ideas you want to share with us, any things you want to hear on this podcast, you know how to get in touch with us. Info@SciStarter.org. Thanks.